Howdy. This video tries to provide an introduction to chemical kinetics. Well, in thermodynamics, we talk about what is more stable, what is less stable, we end up at equilibrium. Thermodynamics and kinetics are completely different. Kinetics is about how fast the reaction goes. Thermodynamics is about what is more stable. And so kinetics is the study of reaction rates. An understanding of kinetics can help us speed up a reaction or slow down a reaction. Understanding kinetics can also be used to inhibit reactions that produce toxic materials. And so chemical kinetics is fairly important. After watching this video, you should be able to identify the differences and similarities between kinetics and thermodynamics. You should be able to identify the four things that influence the rate of a reaction and explain the physical basis of each. You should understand the three different types of rates: instantaneous, average, and initial. You should be able to relate the reaction rate of all the compounds in a reaction to each other and determine the value of the unique rate. And so a question we could ask is a reaction with delta G naught minus 2.9 kilojoules per mole spontaneous or non-spontaneous? Well, according to thermodynamics, if you have a negative delta G naught, that means the products are more stable, and so we'd call that spontaneous, meaning that it occurs without any outside intervention. You notice spontaneous does not mean instantaneous. So we actually do not know whether or not this reaction would be fast or slow. All we know is that the products are more stable than the reactants. Now, an example of a reaction with this delta G naught would be diamonds going to graphite. Now, this graphite is more stable, so we know eventually all diamonds should turn into graphite, but the kinetics is so slow, we do not have to worry about it in our lifetime. And so thermodynamics tells us that the graphite is more stable. Kinetics tells us that the reaction is so slow we don't actually have to worry about it over our lifetime. Now, there's also some differences in terms of the math. And so in thermodynamics, we talked about an equilibrium constant, and we symbolize it with a capital K, uppercase K. In kinetics, we'll talk about a rate law, rate equals K times concentrations of the reactants to some power, and we'll use a lowercase k for the rate constant. And so please don't get confused between these two. It's easy to uppercase K, capital K is equilibrium constant, lowercase k is rate constant. When we did our equilibrium expression, we did products over reactants, coefficients become exponents, and so we could tell the exponents just by looking at the coefficients in the reaction. Now, for the rate law, those exponents have to be determined experimentally, so that's a big difference. And so both the equilibrium expression and rate law, we have exponents for the concentrations, but again, for equilibrium, those exponents come from the coefficients. For the rate law, the exponents have to be determined experimentally. In equilibrium, for general chemistry, pure solids and pure liquids were not included in expressions or expressions for the reaction quotient because their activities were 1. Now, in rate laws, we actually do include solids and liquids. For equilibrium, how temperature affected the reaction depend on if it was endothermic or exothermic. For endothermic reactions, K increases with increase in temperature. Remember, endothermic means heat is a reactant, and so a higher temperature is like pushing that reaction to the right. For exothermic reactions, equilibrium constant decreases with the increase in temperature. In kinetics, it's different. Higher temperature always means faster reactions. And so please make sure that you're able to compare and contrast kinetics and thermodynamics. Now, talking about kinetics, we're typically talking about rates, and there's actually 4 things that affect reaction rates: concentration of the reactants, physical state of the reactants, temperature, and presence of a catalyst. And so for the concentration, typically the higher the concentration, the faster the reaction. And so here we have a 0.3 molar solution of HCl and a 6 molar solution of HCl. And if we put the magnesium inside these solutions, the hydrogen ions of the HCl will attack the magnesium, they'll react, and you'll form hydrogen gas and magnesium ions. Now in the 6 molar, it's going to be easier for the hydrogen ions and the magnesium to come together to react because the higher concentration. So typically the higher the concentration, the faster the reaction. Now on the right, you can see the plots. The top plot is the rate with 0.3 molar. The bottom plot is the rate with a 6 molar HCl. And so we see that the rate of the 6 molar HCl, it's much faster. It takes much less time for it to react.
In the test tubes is hydrochloric acid. On the left is a 0.3 molar solution, and on the right is a 6 molar solution. If we place a strip of magnesium metal in the 0.3 molar solution, the metal begins to react slowly. If we place a similar magnesium strip in the 6 molar solution, the reaction is much more vigorous. Within moments, the reaction is complete.
And so
Meanwhile, most of the magnesium in the 0.3 molar solution is still in solid form.
So in general, the higher the concentration, the faster the reaction. Not always true, but in general, most of the time that is true. Physical state of the reactants also plays an important role, and so the higher the surface area, the faster the reaction.
On the plate is a pile of lycopodium powder. If we aim a flame at it, not much happens. If, however, we take some of the lycopodium and then spray it into a flame, the combustion reaction is explosive. The more surface area of the lycopodium particles that is exposed to oxygen, the faster the reaction.
And so it's kind of amazing. It was the same material. If it's clumped up, it didn't really burn very easily. When it's spread out, it burned much easier. And that's just the physical state. Same compound, but the physical state was a little bit different, and so it made a much faster reaction. Now in the can, in the bottom, they have a funnel, and they'll put a little lycopodium powder in the funnel. They'll push the bulb, they'll push air and cause the lycopodium powder to disperse. And there will be a candle in the can, and it will ignite the powder. And again, this is a demonstration that physical state of the reactants actually matters.
Lycopodium powder is placed in the top of a funnel mounted inside a large can. A lighted candle is also placed in the can. The cover of the can is firmly pressed into place. Air forced into the funnel causes the powder to disperse within the can and to be ignited.
Unfortunately, there are real-world examples of this. Grain elevators can explode if they get too fine of powder around, because the very fine powder is very reactive. And so we saw that the higher the concentration, typically the faster reaction. The higher surface area, typically the faster reaction. So physical state affects the speed of the reaction. Now temperature also affects the speed of the reaction. And if we think every day, the higher temperature, the faster things cook. The lower the temperature, the slower something decays. We put food in refrigerators to cause it to decay slower. It doesn't stop the decay of the food, but it just makes it slower, because lower temperature, slower reaction, higher temperature, faster reaction. Now we can actually look at bleach plus the dye. Bleach plus the dye on the left is 54 degrees, on the right is 22 degrees. Higher temperature should always mean faster reaction. Remember, this is very different from equilibrium, where the effective temperature depends on if it was an exothermic or endothermic process. But for kinetics, higher temperature always means faster reaction.
If we pour equal amounts of hot and room temperature bleach into separate beakers of colored water, we see that the hot bleach on the left destroys dye molecules more rapidly than the room temperature bleach on the right.
And so higher temperature, faster reaction. And so we saw higher concentration, typically the faster reaction. Physical state affects speed of reaction, typically the higher surface area, faster reaction. Higher temperature, always faster with the reaction. The fourth one, catalysts can greatly speed up a reaction. And so catalysts are fairly impressive. They actually just provide an alternative pathway for the reaction. They are not consumed by the reaction. And so in the beaker is hydrogen peroxide, and if you look at the movie when it starts, you don't see any reaction. There is a reaction, hydrogen peroxide going into water plus O2. It's just very slow. Now once the manganese oxide is added, the reaction gets much, much faster. Now what's happening is the reaction is going to occur on the surface of the manganese oxide, speeding up the reaction by like a factor of 10,000 times. Now if we filtered out the manganese oxide, we could actually use it again and again and again, because again, catalysts are not consumed by reactions.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
But catalysts are used in many industries because if you can speed up reactions, you often can save a lot of money. And so catalysts are very important. And so 4 factors that affect reaction rates: concentrations, typically the higher the concentration, the faster the reaction; physical state, things like surface area, the higher the surface area, the faster the reaction; temperature, higher temperature always means faster reaction because the molecules are moving at a faster rate, and so you have more collisions at higher temperature; presence of a catalyst, we'll see later, catalyst lowers activation energy, provides an alternate pathway, and so a catalyst can greatly speed up a reaction. And so of these 4, notice that the concentration is actually in the rate law explicitly, right? The rate law is rate equals K concentration to some power, and so the concentrations are in the rate law explicitly. And so the other 3 are factors that affect the rate constant. And so affects the rate constant would be the physical state of the reactant, temperature, and the presence of the catalyst, because again it changes the activation energy, which we'll talk about later. And so we can determine the reaction rate by just monitoring the reaction in some way. And so for the dye, we can actually probably do it spectroscopically and measure the color as a function of time.
Pouring bleach into a beaker of water and blue food dye converts the dye molecules into a colorless form. The timer indicates the progression of the reaction. If we plot the concentration of dye molecules at various times over the course of the reaction, we can determine the rate of the reaction.
And so the rate is just the change over change of time. Now if we look at a different reaction, very simple, A going to B, and so because you have just one reactant, one product, the concentration of A plus the concentration of B equals. Now A is the reactant, and so its concentration going down if you look at the plot on the right, and B is the product, so its concentration is going up if you look at the plot on the right. And so the rate of the reaction, you have the change of B over change of time equals minus change of A over change of time. That minus sign is important because the rate of change for A should be negative because it's the reactant, and so we add a negative, and that gives us a positive. And delta just stands for change. And so the initial rate, there's actually 3 different rates that we can talk about: initial rate, instantaneous rate, and average rate. And so later we'll talk a lot about initial rate, and so we'll talk about determining the exponents for the concentrations using initial rate data. Initial just means the rate at the beginning. The instantaneous rate can be determined at any point, and instantaneous rate is just the slope of the line where we have concentration versus time. And so instantaneous rate can be determined at any point. Again, initial rate is an instantaneous rate, but it's defined at the beginning. And then the average rate is the rate over some period of time. And so for instance, if we're looking at the green line, so we go from 0.46, so rate of B would be 0.46 minus 0.26. That's the change for the concentration of B, divided by 20 minus 10. That's the change in time, and that gives us 0.02. If we look at the same period of time for A, we get 0.54 minus 0.74 divided by 20 minus 10, and it gives us minus 0.02. Again, the rate of change for A is actually going to be negative because its concentration is going down. The rate of change for B is going to be positive because its concentration is going up. The question we can ask is, here we have this reaction H2 plus I2 going to HI. The concentration of H2 is shown below as a function of time. And so is the reaction rate faster at point A or point B? Well, obviously the slope is more negative at point A, and so the reaction is faster at point A. And so the rate of the reaction actually changes over time. Remember, typically the higher the concentration, the faster the rate. And so you'd expect that over time, as the concentration changes, the rate has to change. Another thing we can look at is, okay, here we have 2NO2 going to 2NO plus O2. Now notice that we have 3 curves because we have 3 things changing. Now which one is which? Well, we assume that the reactants going down, and so the NO2 has to be C. That means A and B have to be the products. Now, according to the coefficient, we should produce NO twice as fast as we produce O2. And so that tells us that that top line is NO, concentration of NO. The second line is concentration of O2. And the third line is concentration of NO2. Now, having three compounds in reaction, having to keep track of three rates is kind of difficult. And so it'd be kind of cool if we could just somehow find a way of combining them. And so we only have to talk about one rate. And that's actually what we can do with a unique rate. And so for the unique rate, what we do is we can actually talk about the rates of each of the compounds in the reaction and make them all equal to each other. And the way we do that is we put negatives in front of the reactants because their concentration is presumably going down. And we divide each rate by the coefficient. And so that way, each of these things equal each other. And so minus 1 over A rate of A equals minus 1 over B rate of B equals 1 over C rate of C, which equals rate of D 1 over D. And again, this is really cool because this way we only have to worry about one unique rate instead of 3 or 4. And so a question we could ask is, which of the following is not a correct expression for the rate of the following reaction? And so again, remember that we need negatives in front of the rates for the reactants. And so that first one is not going to be correct. But all the last three are actually equal to each other, and they're also equal to the unique rate. And so further above the reaction, we can write rate equals minus the rate of A equals minus the rate of B, which equals rate of C, which equals rate of D. And again, because the coefficients are all 1. Now here's a little bit more interesting example. We have 2BrNO going to 2NO plus Br2, which the following is equal to Br2, the rate of Br2. Now notice that that is equal to unique rate. And so we just have to find which of the ones below are equal to unique rate. Now that first one, we have 1/2 BrNO, the rate of BrNO. Now the 1/2 is good. We need that divided by the coefficient, but we need a negative. So it can't be the first one. It can't be the second one because again, it has to be 1 over 2. Now the third one, we got negative. It's a reactant, so it should have a negative sign in front. You should have 1 over 2 because that 2 is a coefficient, so that's good. And then we got the rate of BrNO, and so it's got to be that third one. And so this is the equation for unique rate with all the compounds, and it was the third one. One last example, which compound will have the fastest change in concentration? Now concentrations are always going to be in terms of moles or molarity, and so it depends on moles, and so the one with the biggest coefficient is always going to have the fastest change in concentration, and so that would be the BrNO or the NO. We could also ask how much faster is hydrogen peroxide consumed than O2 is produced, and so one way of doing that is just by looking at it, and you see that coefficient from 2 in front of the hydrogen peroxide, coefficient 1 from the oxygen. So, and you could say is that, okay, the hydrogen peroxide should be consumed twice as fast as O2 is produced, and that makes sense. Another way of doing it is you write down unique rate. You look at the compounds you're interested in, and then you solve for what you're interested in, and we get the rate of change for the hydrogen peroxide is minus 2 times the rate of change for the O2. Now that minus is because the hydrogen peroxide is being consumed and the O2 is being produced. And so the rate of change for the O2 is positive, the rate of change for the hydrogen peroxide is negative. For the following, which is components concentration change is the fastest, and again, the one with the biggest coefficient, and so that would be the hydrogen. If oxygen gas is being consumed at 6 moles per second, how fast is methanol being consumed? And so one way of doing this is looking at it and trying to figure out in our head. And so let's see, oxygen 6 moles per second, and so 6 divided by 3 gives us 2. And then 2 times 2 is 4, and so we should say that methanol is going to be consumed at 4 moles per second. Now, if you don't want to try to figure it out, what we can do is just write down unique rate, look at the compounds we're interested in, and so we're asked about methanol and O2, and so we just take those two, and so we have minus 1/2 of the rate of change of methanol equals minus 1/3 of the rate of change for the O2. Now we want the rate of change for the methanol, so we solve that by multiplying both sides by minus 2. And so that gives us the rate of methanol is equal to 2/3 the rate of the O2. And so our rate of O2 is given as minus 6. Notice that in the problem it says consumed at 6, and so it implies you have a rate of change of minus 6. And so 2/3 times minus 6 gives us minus 4. And so the methanol is being consumed at a rate of 4 moles per second. And so please remember, if you're being consumed by something, if something is being consumed, its rate of change is going to be negative. If it's being produced, the rate of change is going to be positive. If oxygen is being consumed at 6 moles per second, what is the unique rate of the reaction? And so again, unique rate, you have minus 1 over the coefficient times the rate of change. And so minus 1/3, the rate of O2 equals minus 1/3 times minus 6. And so our unique rate is 2. And again, the importance about the unique rate is instead of having to worry about 4 different rates for this reaction, we only have to worry about 1. And it also enables us to actually show the relationship between all the compounds in that reaction. And so kinetics is a study of reaction rates. If you know kinetics, you can actually speed up reactions or slow down the reactions, or possibly reduce how much toxic materials are produced by a reaction. Kinetics and equilibrium are very different. Equilibrium is about what is more stable. So equilibrium is about what is more stable. Kinetics is about reaction rates. And also please remember the differences in terms of math. For equilibrium constants, capital K. For rate constants, lowercase k. For equilibrium expressions, the exponents are coefficients from the reaction. For kinetics, the exponents have to be determined experimentally. I hope that helps.